So I'm going to talk today about, give you sort of a quick summary of where we stand in terms of the early bombardment of the moon and our latest results to this effect. So to start off with.
Would you mind using the mic?
Oh, I would want to use mic. Okay. Is that better?
Yeah.
Okay, I'll do that. All right. So what do we know? So I've gone to lots of conferences with geochemists and people do chronology and the rest. Everybody fights and the rest. And I'm going to give you right now what I think is a reasonable summary of what the field thinks, not what everybody thinks, but what I think the field thinks. This is the consensus, and I'm being a little minimalist here. So I would say on the whole, from Grail data, from the work of Don Wilhelms and many others, there's on the order of about 50 lunar basins on the moon. Okay, the ages of these basins are still in dispute though. And after boiling all this down, I would say what I'm going to say right now is generally accepted. The one basin where we probably have a good age is Imbrium Basin. The Imbrium Basin's on the near side, it's about 1,000 kilometers across. We think that basin's probably around 3.9 billion years old. Okay. There's another basin, which is a little bit younger, which is the youngest, largest basin on the moon. That's called Oriental. We don't have an age for Oriental, but we can bracket its age between Imbrium and some other terrains that have been dated by Apollo samples. And so two of the three basins we have on the moon are also two of the youngest, and their ages are around 3.9 or younger. Okay, so that's what we know. Okay, the oldest basin on the moon that everyone agrees is a basin is this one called South Pole Lake Basin. It's about 2,000 kilometers across. We have no age constraints on it, no direct age constraints on it today. All we can really say from what we know is that it's older than 3.9 billion years ago. There's some model ages and some other things I'll talk about later on. But ultimately, that's the holy grail. We'd like to find out the age of that basin because then that tells us more about the whole history of the 50 basins, and we can use it to constrain some different models. Okay, so what models can we apply? Well, this has been the problematic aspect of this. People have suggested all sorts of models in the literature. They've suggested a cataclysm where almost all the basins formed 3.9 billion years ago. They've suggested that, hey, maybe after accretion, the moon gets hit a lot by accretion, so we have sort of a declining bombardment. There's been hybrid models. I've been involved with these hybrid models. But the big problem we have with all of these is we essentially have no age constraints on these. So we don't know which one is right. And that's because almost all of our samples have come from the near side of the moon, the Apollo terrains, the Lunar spacecraft that brought back samples. We have some lunar meteorites from the far side, but they're not really well linked to given terrains so much. And also they don't really date the oldest terrains that we want. So we need to get more samples from these older terrains to really make progress. Okay, so what I'm going to do right now is, given our lack of age constraints from samples, I'm now going to tell you a story. And the story is where I think we stand right now from the dynamical history of the solar system and how the moon fits into that. So I think the story is pretty good, but there's always changes in dynamics. Okay, so since we have young people in the audience, I'm going to sort of start at some of the basics. I would say that is a reasonable working model that the giant planets that we have today did not form on their current orbits. They formed in different locations, so that the planets Jupiter, Saturn, Uranus, and Neptune formed between about 5 AU and about 17 AU or so. Beyond that, we had a very large disk of material that I'm going to call the primordial Kuiper belt. That was once probably the order of about 30 Earth masses. From that system evolved to where we have it today, where we have 4 giant planets that are spread out, and then we have a population that much smaller, maybe about a Mars mass in the current Kuiper belt or so. So the question is, how do we get from the former to the latter? Okay, and the thinking is that our system went through what's called a giant planet instability. Essentially, Neptune enters that primordial Kuiper belt, it migrates through it, it sends most of that mass into the giant planet zone, and it causes the planets to go berserk. They all encounter one another, they evolve, and eventually they evolve to their current orbits. Now, one of the things we've been finding out over the decades is doing some of this, is that anything that encounters Jupiter is very likely to be thrown out of the solar system. So if we start off with our existing 4 gas giants, you almost always lose our Uranus or our Neptune, which is bad, right? We don't want that to happen. So we tried models where you have 5 giant planets, you have an extra Neptune. These models are very, very successful. They work very well. They allow Jupiter to migrate, and we need Jupiter to migrate for a whole bunch of different reasons, but in the end, we lose a gas giant. Okay. The other issue with this model is the timing of it. When this model was originally proposed, it was thinking, hey, look at all this stuff flying around. I bet this is the late heaven bombardment. And we thought that for a while. But our dynamical models just can't stay stable enough to make that bombardment happen. And there's some other constraints. Big populations like to collisionally evolve, And that doesn't match a lot of the constraints we have from well-separated or Kuiper-belt binaries and the rest. So right now we think that this instability didn't wait hundreds of millions of years, but actually it happened shortly after the gas disk went away. So if this is right, the instability happens maybe 10 or 20 million years after the first solids, but that means it's happening in the middle of terrestrial planet formation. So now we have to worry about that part of it. So this is a model where David Nisforny and his colleagues tried to put together everything that we know. So he allows for terrestrial planet formation, but it's happening during the giant planet instability. And so you can see in this simulation that Jupiter's migrating inward just a few tenths of an AU. That's about how far we think it moved. But what that does is that adds this extra level of dynamical excitation to where the terrestrial planets are forming. So the protoplanets and planetesimals are coming together, but they're getting more excited than they normally would. This actually works very well to give us a Mars, which is about the right size. And if you look carefully here, you're going to see two bodies that are about half Earths that strike one another. And it's very interesting. There are other possibilities, but this outcome is actually surprisingly probable. And that's an outcome that Robin says might actually solve some of our isotopic dilemma we have with getting the Earth and Moon to be very similar. Okay, so this could be right. The other thing I want to point out here is you'll notice that there's all these white dots flying around at the end. Some of these are excited leftover planetesimals from terrestrial planet formation. They are very good at beating up on everything after the moon forming event takes place. Okay. So here are the results from that simulation. David tried many different simulations. This was maybe one of their best fits. So that's what we're going to use here. You can see you do a very nice job of fitting the mass of Venus and Earth and their current orbits. You get a nice mass and distance for Mars. Mercury's off, and our current simulations are getting better on Mercury, but Mercury's not as needed for what we're doing right now. And then this is the asteroid belt over here. And this model actually does a pretty good job of reproducing a lot of the constraints we have from the asteroid belt. So that's good. Okay. So what we did is we took that model, we put in many, many more planetesimals. So 10 to the fifth planetesimals, and we let them evolve. So this is what you're looking at here. So we have Venus, Earth, Mars, then all of these objects that are dynamically decaying away. And then we looked at how often these objects were striking the Earth and Venus and Mars. But we're also tracking how many impacts would happen on the moon. Okay, that was good. And so we put this in with also the same model is allowing for how many asteroids hit the moon, how many comets hit the moon. It turns out leftover planetesimals just dominate these populations. Okay. So this is what it looks like when we put it all together. So what you're looking at is a plot of time after the first solids. So the solar system forms at 0, or if you like 4.5 billion years ago, you can look at the top. The y-axis is the total number of accumulated basins on the moon. Okay, so what we can do is, since we said we have 50 lunar basins, you can take this plot, you can go back in time, and you stop when we get to 50. So that represents that little dot dash line up there. So that says that the 50th lunar basin, or the first one, forms at about 4.35 billion years ago. And that's interesting because there are some interesting constraints that suggest something big was happening on the moon about 4.35 billion years ago. People like Dave Kring and others have argued that's the formation time of SPA. Our model would support those ideas. Okay. But there's a couple interesting things also that come out of this, right? You'll notice that the curve keeps going up. So if SPA formed at 4.35 billion years ago, there had to be many SPA-sized cratering events on the moon prior to that time. So the question is, why don't we see that? And that's going to be a big factor here. There's some other things I can say here, but I think for time reasons, I'll keep moving on. Okay, so if you have all these big SPA type events, why don't we see them? And there's a bunch of different ideas for this, and we don't have the final solution today. Some people have suggested that maybe the moon had an extended magma ocean, and the magma ocean kept the moon from sustaining any craters or anything for some period of time, or it produced erasure events just before 4.35 billion years ago or so. Okay, so we don't know that. There's also people like Lars Borg. Lars is really smart, and he argues that the moon may have formed around 4.4 billion years ago. Dynamically, that doesn't match our models. But whenever Lars says something, I pay attention. So is he right? Or who's right? Are our dynamical models right? Or is he right? And that's something we have to resolve. Okay.
1 minute.
Okay. So I think I have one more slide. So ultimately the question is, can we prove this? And then the other thing with bombardment, if they're all coming from leftover planetesimals, can remnants from samples tell us about the nature of the impactors coming there? Can we prove this hypothesis? So here's, I think, this is my concluding slide. This is just, I think, where we stand on things. So open questions we have right now in this field. When does the moon form? Does it form early or does it form late, as Lars suggests? What's the length of the lunar magma ocean? What happened to these extra SPA-sized basins if this model is correct? Because they did hit the moon. Do we have the correct age for South Pole Lake and Basin? And then finally, can we find evidence from samples we bring back from the moon for the long lost precursors of Earth and Venus and all the rest? That evidence should be on the moon if we get the right samples. So thank you.